The Inter-Society Color Council is creating Fluorescent Fridays as a platform for university students from different perspectives to network with color professionals and fellow students and to explore cutting-edge information about color's multidimensional nature and its application in the world. If you're interested in being part of this, check out our website. Our long-term goal is to build a global student chapter that positions color as a multidimensional STEAM model: science, technology, engineering, arts, and math, and provides up-to-date color research by scientists, artists, designers, industry professionals, and students working at the university level. If you're interested in being part of the IACC, some of the benefits of joining as a student, you will get access as a quarterly ICC newsletter, access to recorded webinars, discount on color research and application, professional interaction with color scientists, industry practitioners in our community. Okay, so today we're going to have 6 guest speakers giving 6 mini talks. And this Fluorescent Friday session will feature next generation color. We will discover different perspectives from students around the world. Get your questions ready for a Q&A session at the end of these presentations. You can write them down in the chat as we go, and then at the end, the panel will answer them. My name is Lina Cardenas, and I'll be your host. I'm an assistant professor at the School of Design at the University Católica de Chile, and also a board member of the ICC. Our first guest is Olivia Kuzio. She is a PhD student in the program of color science at the Rochester Institute of Technology, where she conducts research in the Studio for Scientific Imaging of Cultural Heritage. She has completed conservation science co-ops at the Smithsonian Museum Conservation Institute and the Getty Conservation Institute. She holds a BS in chemistry from the Pennsylvania State University. She will be talking about the multidisciplinary art of art imaging. Olivia, the screen is yours.
Thank you so much for introducing me, Lila, and thank you to our audience for being here. There are some really cool talks ahead today, but I personally think that the coolest part of today is you all and the broad range of interests that you represent. You can see that I consider the research I do to straddle a few different disciplines, and as I continue to learn more about the field of scientific cultural heritage imaging, I only become more convinced that this kind of imaging is certainly scientific in theory, but it's at least equal parts science and art in practice. So scientific imaging is only one of several broader kinds of imaging of cultural heritage. The other general categories are collections photography and conservation documentation. These 3 kinds of imaging are generally very different in purpose, tools, and results. Collections photography is that which is public-facing, and it provides images for things like websites, advertisements, and exhibition catalogs. Conservation documentation is just one way that conservators track changes as they treat and restore objects. Scientific imaging is typically associated with technical studies of artworks. These often support conservation treatments and can answer questions like, what is this material, where is it from, and how was it made? In many cases, then, color can serve a huge role in answering these questions, which is why it's an important facet of many technical imaging campaigns. Because color is so important, multispectral imaging in the visible range is a powerful analytical tool for these campaigns. Not only does it afford killer color reproduction, which is better than what we can get using conventional RGB capture, it also allows us to characterize materials without having to touch them or take samples from them. Both of these features come from the spectral aspect of the imaging strategy. So we're all familiar with the idea that the spectral reflectance of a material, or how much light of each wavelength it reflects, in large part determines the material's color. The reflectance spectrum is also often diagnostic of that particular material, which helps us to identify it. We can measure the reflectance at single points using a spectrophotometer, but if we want to know how the spectra change across a larger area, or even across the entire surface of a painting, point spectrophotometry is going to get really tedious, which is where multispectral imaging and then the larger science of imaging spectroscopy come in. Sophisticated reflectance imaging spectrometers are one of these really hot things in scientific cultural heritage imaging right now. I encourage everyone at some other time to go check out Operation Night Watch, which is just this massive technical study that's currently underway at the Rijksmuseum, and it's largely driven by this technique. However, you don't actually need super high-tech toys to harness the power of imaging spectroscopy for more routine cultural heritage photography. This is the central tenet of my PhD research. Given that multispectral imaging is in many ways still siloed in science labs, we have been working on ways to make it more accessible and relevant for all of these groups. So the purposes of these different kinds of imaging might differ, but that doesn't mean that we can't strive to empower studio photographers and conservators with advanced imaging strategies that improve the quality of the information they're able to capture. We're approaching this with a focus on more practical multispectral strategies using familiar tools, an RGB camera, and multi-channel narrowband LED lights. I definitely don't want you to think that we're shorting anyone. Even these, comparatively simple tools give us a zillion degrees of freedom to play with. And if we use them brute force to their full potential, we actually get more data than is practical for our purposes. So part of the work involves changing our perspective on multispectral imaging from one that's data-driven toward a more needs-based approach. We believe that we can get these tools in the hands of more cultural heritage photographers by putting careful thought into the question, how good is good enough based on the specific purpose of the imaging? Let me give you an example. Here are two images of a painting that I took using our system, and I know that this is not a fair question to ask everyone looking at different displays and different viewing environments, but bear with me. Can you tell a difference between them? Notice that they estimate the spectrum of this magenta color pretty similarly. I'll tell you that the image on the left was rendered from information taken from 10 separate captures, so that's 10 button clicks on the camera, while the one on the right required only 2. Which of these sounds more efficient? Based on profiling the two scenarios, the left image actually does reproduce the colors and spectra slightly more accurately with respect to the real painting. But can we perceive that? And if we can't, does it matter? Maybe a museum photographer aiming to meet a certain standard of accuracy in their digitization workflow would answer that question a little bit differently than maybe a conservator aiming to spectrally match materials for in-painting. So finally, let me just leave you with this. How good is good enough? The bottom line is that it depends on what you need, and to figure out what you need, there are questions and trade-offs to consider, but none that should keep us from democratizing multispectral imaging for broader use in cultural heritage imaging. Thank you everyone for your attention. I'm really looking forward to the Q&A.
Thank you, Olivia, for your presentation. Our second guest is Bill Rios. He has returned to pursue his MFA after 13 years of working as a professional theatrical technician. He has a passion for design and a dream to educate the lighting designers of tomorrow. Bill's work ranges from traditional theatrical lighting design, exhibit design, lighting for camera, theater for young audiences, and community art engagement. He will be talking today about honoring cultural wealth through color in lighting design. Bill, welcome to Fluorescent Fridays.
Thank you so much for that wonderful introduction. As Lina said, my mini talk will be on honoring cultural wealth through color and lighting design. Cultural wealth considers equality, empathy, respect, justice, acceptance, and diversity. You may not know it, but when you go and see a show, whether it's in a theater or at a concert, go to an escape room or a museum, there's a team of people who have thought a lot about how you will perceive that experience. In a typical Broadway show, for example, the main design areas would be scenic, costumes, lighting, media, and sound. These designs create the overall visual and oral experience which support the actors in presenting the story to the audience. My role on those teams is as a lighting designer. Some goals of the lighting design is to help the audience focus their attention, convey time and place, and tell an emotional story through the design. A lighting designer will use the controllable qualities of light in order to advance the logistical and emotional story through visibility. Those qualities are intensity or brightness, which can help focus the attention of the audience, angle or direction from which the light is directed at the subject, shape or edge, which variations include soft or sharp, beams or organic or geometric shapes, time or the transition and how we move from one visual look to the next, and, of course, color, or as we think about it, the set of wavelengths we call visible light. When I construct a lighting design, one of my most important jobs is to create the emotional story through color. I do this through historical and visual research around the emotional journey of the characters that the creative team wants to present to the audience. I typically begin this process on my own, in my head, with my own resources, before I share my findings with the creative team. As a case study, let's look at a show I designed for the Cohen New Works Festival in 2019 at the University of Texas at Austin. As the show description says, Spillage is a contemporary dance work about Asian American women grappling with identity, specifically their relationship to whiteness and patriarchy. Spillage asks how they internalize and perform societal expectations of their identity, what it means to reject certain cultural narratives, and what it looks like to engage yellow female bodies in an amplification of personal collective voice. What the creative team really wanted to express with this piece was how Asian American women are taught to conform to white societal pressure and how their own cultural identity, attributed to the color yellow in this work, spills out from that pressure. I started my research in a typical Western theater fashion of looking at paintings around the color yellow, but it occurred to me that my male Western white trained perspective didn't fit the subject matter of the art we were creating. In fact, it was exactly what we were trying to comment on. The other direction I could have gone was to revolve around my own notions of Asian identity, which are ultimately flawed and orient around the media I consume, which creates a generalization. So how could I gain a footing into this culture that I don't belong to? This is where we can utilize the concept of cultural wealth. Community cultural wealth can be defined as an array of knowledges, skills, abilities, and contacts possessed and used by communities of color to survive and resist racism and other forms of oppression, as defined by Tara J. Yoso at the University of California. So I sat with the director and dancer, Becky Nam, pictured here, and the choreographer, Emily Tolson, and we created a color palette based on their reactions and feelings to the piece. Luckily, we had a completely color-changing lighting rig in the studio we were working in, so I could dial in colors for them and ask if this was the white that they were seeing when they pictured the idea of white societal racism, or is it this one? Was this the yellow they envisioned spilling out from the social pressure, or did it have a little bit more red in it? Through these conversations, we were able to create a color palette to work from, which enhanced the connection between the dancers and the audience through the culturally informed color story we created together. In the next slide, we will watch a clip showing the climax of the piece that exhibits the range of colors we chose. In making this composition, we received a wide array of feedback from advisors, including one that told us the piece didn't look Asian enough. But the team decided to follow our instincts and honor the expertise and cultural wealth of the Asian American women creating the work. Honoring and engaging with cultural wealth of a community you do not belong to is a strategy that lighting designers can use to recognize cultural ties to color. As storytellers, we can learn to let go of our own personal narrative and let other communities be co-creators in our art. This process can be valuable in building an anti-racist practice in our art making and storytelling. Through this, we can create cross-cultural understanding that will build equity, respect, and acceptance. Thank you so much for your time and attention.
Thank you so much, Bill, for that wonderful presentation. Our third guest is Soojin Lee. She just submitted her doctoral thesis at the University of Leeds. Previously, she worked as an interior designer in South Korea, and she's currently working as a postdoctoral researcher for the Instant Design Project with Axo Nobel. Today, she will be talking how individual differences influence effective appraisal of color environments. Soojin, the screen is yours. Welcome.
Hello, everyone. I'm Soojin Lee. As just Linda introduced me, I just passed my PhD Viva last week, so I'm really feeling happy now. Currently, I'm working as a postdoc at the University of Leeds on a color design project with Axo Nobel. Before I start my PhD, I worked as an interior designer in South Korea. My PhD was about the preferences that people have for the color and atmosphere of their working environment. I focused on creative work, so many of the participants in my studies were creatives. At least we have a lighting system which can change the color of the room wavelengths by wavelengths. So here you can see my supervisor, Professor Stefan Westerland. I constructed a working environment within the lighting booth so we can do experiment with a different light in the room. For example, in my MA project, I looked at the effects of color on heart rate and blood pressure. One of my study for my PhD study, I asked 142 people what attributes matter to them for their creative working environment. The box plot you can see here summarize the result. Participants indicated the importance of each attribute using a continuous scale. The 24 items were selectively chosen from Vogel's atmosphere matrix. Here on the x-axis is the 24 atmospheric items, and the y-axis is the range of scores between 0 and 100. This diagram indicates that each variable shares some common variance with the others. Attributes that were strongly preferred were comfortable and safe. Attributes that don't matter include mysterious and former. People have a good idea about what they want.
Soojin,
Yeah.
could you put your video on? We want to be able to see you, or we can't.
I feel a little bit comfortable without showing my face for this presentation. Is it right?
Okay. Just wanted to ask you. That's okay.
Thank you. Yeah. 30 Japanese undergraduate students took part in a photo simulation experiment. Why Japanese? Honestly, I had to visit Sato's lab in Japan. If I had the chance to go a different country, I would have done in there. The participants were asked to evaluate the effective value of the 12 different light environments in a laboratory based on the 6 factors found in this survey. because we couldn't transfer that the lighting system at Leeds to Kyoto. So this part of the study was done as a virtual simulation. I then use exploratory factor analysis proceeds to identify common themes in the 24 atmospheric items. The exploratory factor analysis is a process to reduce data to a smaller set of summary variables. From this, I could identify 6 factors: comfortableness, pleasantness, inspiration, personalization, restrictiveness, and chickeness. Overall, these are the factors that matter to people. I have lots of data, but as just an example, here are the data for comfortableness. Here on the x-axis is the color of the environment, and the y-axis is the mean values. The higher the score here, the more comfortable. Notice here, the left, the red is on the left and blue purple on the right. Maybe people will be surprised that yellow lighting was most comfortable and purple, magenta, and red were uncomfortable. In addition to asking about my 6 factors, I also asked about their general preference for each color environment. Comfortableness and general preference were highly correlated. Here are the main study findings. In addition to the overall negative impression to purple, magenta, and red light, and the positive impression to yellow light, there was an interesting finding of a bluish light environment. For example, blue cyan and blue light environment were evaluated to be personal and chic. For the attributes personal and chic, the score for the blue cyan and blue light were substantially higher than those in other color environment. Before to wrap up the presentation, I would like to mention the most important thing I learned during my PhD studies. Doing a doctoral research was an eye-opening journey for me to discover and develop the inner qualities that can push you through no matter what the obstacles are. One of the biggest lessons I've learned is that the main key to succeed is not cleverness, talent, or luck, but having the personal, insightful mindset of a grit, even when I face barriers and fell down. I think it makes all the differences. So whatever you do and whoever you are, I wish you find and cultivate your own grit in your own race. Yeah, thank you for your time and attention.
Thank you, Soojin, for your presentation and to share that interesting work. Our 4th guest is Francis Pellegrino. Francis is currently in his 3rd year studying optical engineering at the University of Rochester Institute of Optics. He also serves as a co-founder and CEO of Advanced Growing Resources, AGR, a startup engineering innovative optical sensing solutions from agriculture. He's going to talk how the advantages in color measurement technology can be implemented in the field of agriculture. Here now is Francis Pellegrino. Welcome.
Thank you for the introduction, Lina. Let me share my screen. Well, it's an honor to join all of you here from the University of Rochester. And as Lina said, I'm currently in my 3rd year studying optical engineering, and I also serve as the CEO of Advanced Growing Resources. My fellow students, Harry Raja-Oberson, Andrew Thankson, and I have come together from 3 different countries spread across the globe to help solve one of agriculture's biggest problems with a healthy dose of color technology. More specifically, we analyze the spectrum of colors reflected from leaves in order to determine key factors of plant health and growth. Now, this is important because crop affliction is a $220 billion a year annual problem, according to the UN. Now, if I were you right now, I'd be thinking, but I'm an engineer, I'm a chemist, I'm an artist, I'm not a farmer. But no matter what we do or where we're from, your next meal is never very far away. In fact, it probably came from a field just like this, where growers keep their plants healthy by mass spraying pesticides and fertilizers. But that's a big problem. The chemicals that coat produce aren't healthy for consumers. The mass spraying process takes time and money on the part of the grower, and chemicals that are absorbed into the soil are either converted into greenhouse gases or simply poison the ecosystem. All three facets of this problem became clear after conducting more than 150 discovery interviews with agricultural professionals across the United States. Even more importantly, they also expressed a desire for new methods to detect crop afflictions early, before they spread, that can guide more targeted application of chemical solutions. That's why we've created the Ag Quarter. Our patent-pending scanner is a handheld dual spectrophotometer and imager which analyzes colors reflected from a leaf that are either indistinguishable or simply invisible to the human eye. The scanner is used in conjunction with our mobile and cloud-based software for advanced data analytics. We essentially bring standard lab testing to the field to avoid weeks of waiting and limited sampling so solutions can be provided when and where they're needed. In light of the pandemic, this is akin to the transformation of rapid testing. Now, as many of you probably know, spectroscopy is not fundamentally a new technology. So how is the Ag Quarter a step forward? It all comes down to three things: portability, affordability, and usability. Previous systems, like the one on the left, required a fully loaded rig, thousands of dollars to invest in that equipment, and an operator who was skilled in the art to gather and analyze data. That might be accessible to a handful of color specialists, but not for members of other professions who need just as many capabilities. That's why we're developing the Ag Quarter as a handheld device that can be sold for under $2,000 with a user-friendly application. The foundation for this is made possible by recent advances in affordable microspectrometers and color imaging detectors, in addition to the pocket computing revolution that's been launched by the standard smartphone. I'll stick to the color tech for now, though. Our spectral detector separates incoming light into its constituent wavelengths, similar to a rainbow or a prism. Those, however, are based on refraction, or bending light, while we use diffraction, or dispersing light. A diffractive optic similar to what's used in the Ag Quarter spectrometer is shown here. It looks like a mirror, but advances in holographic lithography have made it possible to etch fine diffractive structures onto the surface with a process that enables mass production. The ability to manufacture these diffractive mirrors, called concave holographic gratings, at scale has led to a new evolution of spectrometer design. As you can see on the right, this single element can now replace the bulky and expensive chain of optics that comprised the previously standard design. Instruments that used to be the size of a brick can now balance on the tip of your finger at a price point that falls within the range of installation into high-end consumer products. At AGR, we've left the development of our spectral detector to one of our corporate partners who has advanced manufacturing capabilities. Our team integrates it with proprietary optics that serve as the eyes of the system, combining that spectral data with additional imaging capabilities to feed powerful results. Here, you can see the reflectance spectrum obtained from a leaf plotted in one of our field tests. Please note that this is an early version of our device. We're currently nearing the end of a redesign process for the next iteration, which includes smartphone integration and color imaging capability. These will assist in the analysis of the reflectance spectrum with a variety of published and proprietary indices. Those can be used to pattern match to known spectra correlated with key factors of plant growth and health, such as chlorophyll content, nutrient concentration, and crop diseases. The results can then be presented to the user as either a simple number or on a scale of low, medium, high compared to healthy standards. Now, what you just saw was step one of the process that a grower would use to manage their crops. After collecting data, users will then be able to upload it to the cloud using our software application. Scans can be stored there for future reference and more advanced analytics, such as field mapping, predictive models, and others that can assist growers in planning the application of their solutions. With proper sampling and frequent analysis, crop afflictions should be able to be identified before they spread so that chemicals can be applied in a targeted manner that saves time and money while helping to produce a more valuable and organic product. I would like to give a special thanks to our research and entrepreneurship advisors, Professors Duncan Moore and Professors Greg Schmidt, in addition to my color technology professor and ISCC director, Zhang, who invited me to give this presentation. With the support of generous student grant funding and accelerator training from the National Science Foundation, VentureWell, and the University of Rochester, we will be working full-time next summer to complete initial production and beta testing of the next generation of the Ag Quarter so the world can see the invisible with AGR. Thank you.
Thank you so much, Francis, and congratulations on that project.
Thank you, Lina.
Our fifth guest is Nian Zhang. She's a 4-year PhD student in the Color Science and Imaging Laboratory of the Wilson College of Textiles at NC State University. She hails from China and is interested in color science, imaging, and computer programming. Today, she'll be talking about color segmentation and its application in color quality control of textiles. Let's welcome Nian Zhang.
Thanks, Lina, for your introduction. So I will share my screen. Good afternoon, every guest. I'm Nian, and I'm very honored to be one of the speakers today. My topic today is about color segmentation and its application in color quality control of multicolored textiles. Digital printed textiles suffer from printing defects in the process of manufacture. Improper ink viscosity, irregular substrate surface, and many other factors could cause the color quality not satisfied against the standard. For example, the observer may see a visible color difference between the brown color on the standard sample and the brown color on the batch sample. In that case, he or she will have high possibility to fail the color quality of the batch sample, since the color variation is not desirable in production. To evaluate the color quality in textile industry, there are usually some subjective evaluation involved. In industry applications, color quality control is important for color reproduction purposes, while the reproduced colors are required to be correct when viewed by the observers. The most intuitive way to assess color quality is to ask a human observer to either view the physical samples inside the viewing chamber or a color calibrated monitor. The figure on this slide shows how an observer measures the quantitative perceptual color difference via the grayscale method. Another way to assess the color quality is through instrumental measurement by obtaining its spectral information in the visible light spectral range of wavelengths. Since the physical properties required to describe a color prior to its perception could be determined via the interaction of the light, the sample, and the light source. Spectral information is obtained using spectrophotometers or radiometers. Tri-stimulus values are common parameters obtained through this instrument, and the reflectance spectrum is also obtained as the intrinsic optical characteristic of the colored object. However, this instrument usually have limited size of apertures, and it averages the colors included in the aperture area during the measurement, which results in not a very accurate and efficient way of measuring the multicolored pattern objects. A third way is to apply an imagery-based colorimetry to measure the colors of a large-scale multicolored fabrics by analyzing its digital images. Considering the limitations of the traditional measurement techniques, imaging-based colorimetry is an advanced methodology in textile industry to measure the colors of large-scale multicolored fabrics by analyzing its digital images. Its advantages in high measurement efficiency over the traditional methods, including spectrophotometry and human observations, since it could measure the overall appearance and all colors assessed simultaneously. People take the advantage of the accuracy to conduct color quality control of complex pattern images through this way nowadays. Aside from color accurate and efficient color measurement of multicolored objects, accurate clustering of the pixels based on color features is another important task before color quality control. For example, if you want to compare the individual color on the standard fabric and that corresponding color on the batch fabric, the first step is to segment it from the other colors. Color segmentation plays an important role in imaging-based color quality control of textiles, especially for multicolored materials. To evaluate these individual colors from a multicolored sample, these images are captured first, and the colors of each pixels are measured by the imaging system. Once the color segmentation algorithm separates the colors in the multicolored images, the segmented colors could be compared to its standards respectively in the color quality control progress. And of course, the segmentation algorithm is robust to separate colors of multicolored fabrics regardless of the number of colors, the patterns of the fabrics, or the texture of the fabrics. However, several factors influence the color segmentation of textiles, including color spaces for separating colors, textures, color edges, and transitional color regions. All these factors make this process challenging. Here is a visualization of how the color features of pixels from the same image are distributed differently in different color spaces. The visualization in the multicolored sample in different color spaces has given us an overview of the data distribution and help us choose a color space according to our algorithms. Ideally, we would like to choose a perceptual uniform space to conduct segmentation. Of course, there are many more challenges in the color segmentation research area, and the development of this research has helped us developing a more efficient and accurate way of measuring color qualities of complex pattern colored objects. Thanks for your attention, and I hope you enjoyed the mini talks today.
Thank you so much, Nian, for that lovely presentation. Our last speaker is Sofia Inostroza. She's an integral designer graduated from a Pontificia Universidad Católica in Chile, 2019. She's deeply passionate about all areas of design, interdisciplinary work, and its impact. She's currently working in Will of the World as an UX UI designer and helping make the world accessible. She will be talking about the application of violacine from Hantinobacterium lividum. Let's welcome Sofia.
Thank you, Lina. Awesome, thank you. Okay, so the textile dyeing industry is one of the oldest ones, and up until today is present in our daily lives through the clothes we wear and the textiles that surround us. Its continuous friction with sustainability has triggered an important search for generating new dyes that are eco-friendly, safe, and aesthetic. Some of these sustainable pigments come from plants and also microorganisms such as bacteria. Bacterial pigments have been sought after since they have many clinical benefits and are easily manufactured. Violacine is one of the pigments that has had a growing demand with antiviral and antifungal benefits. And also it has been claimed to not need any additional chemicals in order to adhere to fibers, which signifies a big competitive advantage. So that's how I began this investigation. My name is Sofia Inostroza, and today I'll present my bachelor thesis, which was guided by Lina Cardenas. This investigation consisted in designing 3 methods for dyeing with a bacterial pigment in 6 different textile fibers. Why? Because there's an important search for generating products that protect people, especially given today's context, products that are sustainable, and also so we can create multidisciplinary knowledge about these processes and its aesthetic possibilities. So I contacted Dr. Mario Tello from University of Santiago. and worked with his sample of J. lividum, that is a type of bacteria that produces violacin. He actually took it from he took the sample from the outsides of Santiago in Cajón del Maipo. He let me carry out the experiments for several months in his lab, where for every set of experiments, I had to carry out 2 simultaneous processes. A growth process for the bacteria to produce the pigment, which was a method designed by the biologist in that lab, which I replicated, and then the dyeing processes with the biofilm that contained the pigment, which was designed by me. So one of the dye methods I defined was the direct method. In this method, I tested sterilized fibers submerged with the bacteria as it was growing and producing violacin. This is one of the set of experiments I did, which I had to iterate many times in different set positions and jar sizes. Also, in another set of experiments, I tested laser printed acrylic templates together with the fiber and the bacteria in order to see if this element was able to control aesthetic configurations in the fiber, or if the bacteria surpassed it, which actually met halfway. The second method, which is the padding method, included trespassing bacterial pigment onto a fabric surface. A very interesting insight here was that the composition of the biofilm on the textile was different every time because it is not compact. So when doing this method, you could see different patterns every time. So these are some of the first approximations with cotton, where you can see that the tonality of the color is cumulative. So for nylon, the same thing happened, although the color was much darker and a wider set of tonalities was achieved, as well as the aesthetic configurations due to the structure of nylon. Finally, the third method was the reduction method, which included trespassing biofilm onto the fabric and then carrying out a reduction oxidation process with different agents. So what happens in this process is that once you put the colorant with the fiber in the bath, the colorant molecule breaks. So this happens because of the reaction with the agent. And then once the fiber is taken out and has contact with air, the molecule unites again, closes. So the colorant is fixated to the fiber. So for this set, the best result was from nylon, since the rest had no affinity whatsoever with the reduction agents because they were too strong. Here are several samples of nylon done, in which you can see the results are pretty much the same. So color measurements were carried out using an X-ray spectrophotometer. Additionally, color, light fastness to crocking and to laundering were evaluated. For light results, data showed that nylon expressed the darkest color, while wool expressed the lightest one, followed by viscose. For the direct and padding methods, silk was optimum in washing, linen was optimum in crocking, and for the reduction method, it shows that nylon had an optimum color fastness in washing and cotton in crocking. So the results obtained here show the possibility of using violacin in 3 coloration methods, and these processes may be carried out in a handmade procedure. So experiments indicate that violacin has a high affinity for nylon and a low affinity for wool. Also, nylon had a spontaneous characteristic to its aesthetics in comparison to other fabrics due to its elastic structure. The best control method was padding due to its cumulative characteristic. The one that created the most accidental aesthetics was both direct and padding method, being the direct one more spontaneous, since you're completely letting the bacteria take over the design, and it's like a co-designer. And for the best fixation, the reduction oxidation process was optimum for nylon. Further work needs to be carried out regarding the reduction method and the type of additional agents to use in order to improve color quality. Thank you so much.
Thank you, Sophia, for that lovely presentation. Now, I'll invite you to ask questions to our panel through the chat. Luan, or can you help me?
Yes, and while we're doing this, please, everyone, we're asking you any insight or feedback you have for everybody who's here. Just let us know, like, one thing you learned or what you liked about it. We had a question. It was Olivia was answering it first. It was the first one for her, and that was, what was the advantage of her research, in color, in getting measurements of color. And I know you worked for the Getty Museum over the summer, and so if you could just give us a sense of what were they looking for? What is that? How does that help a museum?
Sure. So I mentioned two important things in my chat answer that I'll reiterate here, and maybe I'll flip-flop them. So probably first and foremost, for conservators who are doing any sort of like, think about in painting or restoration work on a painting that's had paint chipping off or something, if we can use this kind of imaging to identify the pigments that are present there, we can let conservators know what actually that material is, so that they can use, if not the same material, then a material with similar spectral properties, so that it's going to look the same. It's going to match the material that's original to the painting, right? And then hopefully, if you are restoring an object with materials that have the same spectral properties, they'll age in the same way, so that as the pigments age and maybe fade over time, the restoration won't look different than the original as things change. So that was one thing. And the other thing is that we can quantify how pigments and how different materials fade over time. And doing that, so imaging, over a certain lifetime can tell us how colors change. And that can be really important for informing exhibition guidelines. So things for light levels and light duration all go into the whole gallery experience and designing exhibitions. Those are just two things.
That's really interesting, Olivia. And you just got a question from Michelle Habeck, who asked you, is the reading process that you are studying only able to read the surface pigments, or might you also view layered or mixed pigments?
So since we're working in the visible range, we don't penetrate very far into the surface of materials. That's more in like longer range. So IR imaging, you'll get subsurface imaging and be able to visualize subsurface. So not in the particular color imaging that I'm doing.
So this is one of the things that's so interesting about what I'm learning. And I mentioned I'm a painter, so I'm learning all these things from colors to science. And as Lina said, with looking at science, at color in a STEAM way, so science, technology, engineering, arts, and math, you really now get to see how we use it in the world. And most of us don't know or don't realize, how it's used, outside of, just basic paint. So that leads me to another question. This one is for. Let's see. Let's see. Well, let me ask Francis this. Francis, you were the question about how your tool is used in the field and the advances in the technology that you're going to be able to use. I know there was a question when we had the practice session. There are instruments out there, and you did mention, the advances that you are doing, and I'm guessing, can you give us a little more about like how you realized there was this gap and what you could do to actually take it to the next level?
Sure. So after talking to a lot of customers, we found that what most people are currently using, which is hyperspectral imaging cameras on either drones or tractors, those are cameras that divide up the spectrum into a small number of components, maybe 9 to 12 channels. But the problem is there's always a trade-off between spectral resolution and spatial resolution. You only have so many pixels on your camera, so many buckets to put your light into. And you can divide them any number of ways, but if you're splitting it in between looking at more spatial resolution or more spectral resolution, it's always a fight to get enough resolution on both channels, both parts. And so that's led to those kinds of solutions not really being good enough in either way, not a good enough imager and not good enough spectrally. And that's what we've tried to solve in our device. So it's handheld, which means you can get it directly up to the plant and directly up to the leaf. So already you're looking at much better resolution. It's almost like you're using a microscope instead of a telescope. And then when it comes to spatial versus spectral, we've split our detectors into two, and that gives us a lot more resolution on both. Now, there are always compromises, but this is our solution that we think is going to be a lot more effective and a lot more versatile. And that's in fact how we just got our patent, or rather we've just filed for our patent. We're patent pending as of last week.
That is so exciting. It was just so cool to be able to have, we get to hear of that. And that kind of leads me to an interesting comment by Fabian Estrella to everyone. And this was after our last presentation. He said, I love the concept of co-designing with bacteria. It's a really different production process from what's stabilized. Now that question then would go to our last presenter, I think. Just talk a little bit more about co-designing with bacteria.
Yeah, so for the direct method, that was the main one in which bacteria co-designed. So it also depended a lot on the affinity it had for the different type of fibers. And so another factor is also the composition of the biofilm itself. It's different every time you cultivate it. So in some areas of the fibers, it grew. In some other areas, some of the components of that biofilm stayed, and in others it didn't. So then you had a different aesthetic configurations, and that is how, since the bacteria was actually growing together with the fiber, it was producing different designs.
Well, it sounds like you're answering a question that Vivian asked you, which is, she said, I would like to know what was a real discovery for you, what made you happy?
Yeah, that a microorganism might be the next level solution to an existing problem, and that we as designers from our discipline, we can aid science in co-designing with microorganisms in transformative ways. So our role there is also very important.
So that was like, I mean, that's a wonderful discovery. That's this wonderful blend of science and nature and design. I mean, I think that I know we're 2 minutes away, but there's a question for, well, I certainly for synthesizing this, but for Soojin. Soojin, we want to see you actually.
Yeah.
Okay. And now you could turn your mic on, I mean, your video on, I think, so we could see you. But could you just give us a little bit more? You talked about the room that you have in Leeds and the design room. And I know you put in and what that's like, and you showed a picture of that, but just give us a sense of, when you, actually, can we see your video? I still don't see your video.
Okay.
But yeah, it was really interesting for us to find out that there is these rooms that you can use to change the lighting. And yes. I just want to know if you could tell us a little bit more about that.
At least we have the lighting system. So we can change the color of the room. So any purpose of the research, the aim, for example, some of the student, she has interest in the depression. So she would like to investigate how people would feel better if we use different color lighting. For example, is like that. And some of the students to explore like arousing effect. For example, how people can change their physiology. For example, the heart rate, blood pressure. So we would like to explore more about how the different color lighting can affect our well-being. That's the main things we are exploring for now.
Very interesting. Yes, and there was a question to you from Anku from RIT. We still can't see your video, but was there an emotional baseline for the observers prior to the start of the experiments?
Before we started that experiment, we asked about their general emotional state first, and then we measured again after some tasks, the activities in the lighting room. So we measure that changes, the differences between the two times of period. Yeah.
And how did you measure them?
We use the subjective measurement tool. It's a psychological metrics tool. Yeah.
Oh, we're going to have to learn more about that. I know we're at 3:01. We had a question for Nian. Can we just close with that? Nian, this is a question. Could you tell us how your imaging system compares to expert visual analysis of color?
Yes, of course. Thanks for the question. Actually, we are developing the imaging system that can replace the traditional instrumental measurement like spectrophotometers and radiometers. So actually, there are two different kinds of ways of assessing color. So the expert visual analysis of color is subjective, while the imaging-based system and the instrumental-based system are objective. So on the expert side, like people may have different opinions on the color assessment, while the imaging system only gives you an accurate measure of the color quality.
Wow. That is so interesting. I think, you know, I just want to say to everyone who's here, all of our guests and our presenters, it was so interesting to hear from everyone, you know, from design for lighting in the theater, all the way to these very specific ways that you can study color for lots of different reasons for the betterment of our world. So thank you so much to everyone. And for all you presenters, a round of applause to all of you from every one of us. Thank you so much. And, you know, may your research continue and to put beautiful color in the world. To everyone who's been presenting, who joined us today, thank you so much. And we look forward to seeing you for the next Fluorescent Friday. So stay tuned. And be
yeah. Thank you, everyone. And then please save your day for our next event, which will be Friday, June 25th. We will continue with this mini talks. But this will be our second series of mini talks with students from around the world studying with color. So if you would like to share your research, please contact us. Thank you, everyone.
Thank you, Lina. Take care.
Thank you.